Okay, so in order to understand periodic trends, what you really need to understand is the effective nuclear charge. So the effective nuclear charge, ZF, is really the charge that an electron feels. Okay, it can be different than the actual nuclear charge. So the actual nuclear charge is pretty simple. It's just the Z, which is your number of protons, right? So in the absence of any other electrons, right, if you were to look at, say, I don't know, sodium, which has 11 protons, right, the charge that you feel, effective charge should be plus 11. Okay, it's not, however, because the other electrons play a role. Okay, there's this shielding that needs to be taken into account. And that's the fact that if you are sodium and you're the last outermost electron, which is sitting in that 3s orbital, okay, the 2s, the 2p, and the 1s have all been filled, and all those electrons are at least part of the time in between you and the nucleus. So while there's 11 protons pulling on you, those other 10 electrons in the atom are consistently sort of in the way and therefore shielding you somewhat. Okay? So one of the major things to think about here is you're going across a row, therefore, okay, as you move your way from left to right, you're increasing the protons, but you're adding electrons sort of in the same vicinity, okay, in the same orbitals. And since that's the case, they're going to be shielding much less than ones that are far inside it, that have a principal quantum number much smaller. Okay, so as you go to the right, your effective nuclear charge is going to increase. Okay, in general, as you go down a column, okay, your effective nuclear charge is going to increase, but a lot slower than as you go across a row, and therefore you don't need to worry about that as much. Okay, but this is what's going to play a role in dealing with things like ionization energies and radius, etc. Okay, those outermost electrons are not going to be held as strongly as you move towards the left side of the table, right? As you move to the right, where the effective nuclear charge increases, they're held much, much tighter. Okay, and going down a column, one of the things to keep in mind is that those electrons are, every time you go down in a column, even though the effective nuclear charge may be increasing a little bit, because they're so much further away from the nucleus, it's still going to be bigger atom, it's going to be easier to take away the electrons, and so that'll play a role in those factors as well. Okay, so if we look at atomic radius as the first thing, one quick note about this, these charts are coming, you can see it's got a Creative Commons license on it. It's a freeware textbook that, in a sort of strange case, the author and publisher have asked to have their name removed from, but it was originally published under Creative Commons license and therefore is freely available for use. So I'll be citing as Creative Commons and giving the licensing, but not listing the author and publisher since they requested that they not be named. So if we look at this right here, we have a calculated atomic radius, okay, and we're going by atomic number. So we're going to start at 1, which would be hydrogen, okay, and helium is right here, and it's going to drop from hydrogen to helium. Notice the big jump as we go to 3, which is going to be lithium, okay. That big jump is because at this point we've gone out from the 1s to the 2s now. We're a whole another shell out, so this is going to be further away from the nucleus. But as we work right across this row, right, the effective nuclear charge is going to go up, go up, go up, go up, because we're adding more protons with some shielding, but not nearly the same level of shielding you get as every time you would jump a column. So we have this sort of rapid decrease down here, and you come down to neon, okay, which is actually quite small. Next one is going to be another alkali metal, sodium in this case, so once again we jump up in radius. Okay, that same trend is going to continue, fall down. We're going to jump up to the next one, to potassium, and then it's going to fall all the way through the D block, all the way through the P's. Okay, jump up again. So what you see is that in general, elements far over on the right are going to be a lot smaller than elements on the left. And as you go down a given column, the elements are going to be larger as you go down. You know, they might have a slightly higher effective nuclear charge. They're another whole energy level out. Right? Our principal quantum number has gone up each time. Here it was n equals 1, n equals 2, n equals 3, n equals 4, 5, 6. Okay, keeps increasing. So therefore, the radius will keep increasing. If we're going to talk about ionization energy as well, we have another case. Okay, so here ionization energy, we need to understand we're dealing with the first ionization energy, which means only to remove one electron. So we're trying to make these elements be +1 charge. Okay, the neutral form of the element. So one of the things to remember about ionization energy is that what we're measuring really is how much energy it takes to take that electron out. And therefore, the more tightly held it is, the higher the ionization energy. So if we look at hydrogen, it's actually pretty hard, but as you go to helium, that increases a lot. And that's again because effective nuclear charge is higher, it's holding on to its electrons tighter, so it takes more energy to take one away. Okay, as you drop down here to lithium, okay, that drops down, we're going to see this increasing trend as we work our way right across the row because, again, effective nuclear charge is increasing as we go to the right. We're holding the electrons tighter, and therefore, as you try to take an electron out, okay, it's going to be harder and harder to do. The same thing here, okay, in the third row, going up to argon, and through the D block to here, okay, up to here. Now, one of the things you'll note, and that we'll talk about, there are certain exceptions to this. So if you look right here, okay, that is happening right in between nitrogen and oxygen. And so instead of following a nice linear periodic trend up and down, let me just circle that, and that one, and that one. Instead of following a nice linear trend up, there's actually a little bit of a jump. Okay, and the reason for the jump is, if you remember, when we're talking about orbitals having half full and full shells being more stable, okay, at this point this is the jump from 3 to 4. So in the case of this one right here, okay, that first one, we are looking between nitrogen and oxygen, right? Well, if we were to write out nitrogen, okay, it's going to be 1s2, 2s2, 2p3. And oxygen would be 1s2, 2s2. You could also do the noble gas core and just say helium, but it doesn't really matter at this point. 2p4 for oxygen. So to remove one electron from nitrogen, we are going to change that 2p3 down to 2p2. To take one away from oxygen, we would take the 4 and run it down to 3. Well, it turns out that it's easier to take off the one from the oxygen and make it 2p3 because we're going to be a little more stable with a half-filled shell than we were removing an electron from a half-filled shell and making it 2p2. Okay, it's important to remember there's still both a good amount of energy. If you look at this first ionization energy right here, we're still talking, 1,300, 1,400 kilojoules per mole here. So it's not like we're just washing this out and it's nothing. It still takes a lot of energy. It just so happens that in these three cases, between nitrogen and oxygen, between phosphorus and sulfur, and between selenium and bromine, we have these exceptions that are occurring. Okay, and it's important that you just at least understand why that is and be able to talk about those cases. Alright, so that was just for first ionization energies. Now let's talk a little bit about second ionization energies, because that's going to become kind of an interesting thing to look at. So if you take your first ionization energy, that's to take off one electron. Your second ionization energy is to take off another one, and therefore your second. Okay, third ionization energy would be to take off number 3, fourth 4, fifth 5, etc., etc. Okay, so if you look at these values, okay, one of the things you'll note is that here we have an element in the third row of the table. So we're just given that it's a third row in the periodic table. So somewhere in between here, sodium, magnesium, all the way out to argon. It has the following ionization energies: 578 kilojoules per mole. 1,820 kilojoules per mole is the second ionization energy. 2,740 kilojoules per mole is the third, and 11,600 is the fourth. One of the things you'll note is that every single ionization energy and a successive ionization energies here increases. That's because once you take one away, right, you've taken away some of the shielding, some of the repulsion there, and you have not taken away any protons, so there's a higher effective nuclear charge for the next one in. Okay, what you're looking for in this case is a big jump. So we go 578, 1820, 2740, 11,600. So that 11,600 represents a pretty large jump in ionization energy. And what that means is you're taking that fourth electron, in this case, off something that is substantially stronger hold on it than it did the previous three. Okay, so if we look at our row right here that we're looking at, what we're really looking for is something where the first three come off reasonably easy, and then it's very, very hard to take off the fourth. So if you were to start over here at argon, okay, let's say take off 1, I would go to the same as chlorine, so I would be at 3p5, 3p4, 3p3 would be, this doesn't really seem to make a lot of sense why the third to fourth then would be a big jump. If we, however, start with aluminum, especially if we know we're taking them off relatively easily, going to be something forming a positive charge, removing the first one gives you 3s2, removing the second one gives you 3s1, removing the third gives you 3s0, or essentially the same as neon, but then that fourth one, we're now going to have to take it out of the 2p orbital. Right, so we're dealing with aluminum, which has 13 protons in it, and we're trying to get it to an electron configuration that is similar to fluorine. Okay, it's not going to want to remove the one from the 2p. Those things are held in very, very tightly, and that's why you see this drastic increase. So what you're looking at here is the element is most likely going to be aluminum, and the reason we know is because that third jump is the fourth jump, sorry, is so high, and that means that you're now taking out of an entirely new and very difficult shell. Okay, the last one we're going to look at is electron affinity. Electron affinity is essentially the taking a look at the energy required or released, actually. It could be either one in this case, depending on whether the element would like one or not. But it's the energy related to the movement of an electron into an atom. So we're going to take it from another atom and add it in. Okay, so in this case you're going, unlike ionization energy where you're creating a positive ion, in this case we're creating the anion, the negative. Okay, and generally electron affinities are going to become more negative as you go across the periodic table, meaning it's going to release more energy as you go across the periodic table to the right. So, you know, if you look at this, it's increasing up towards the top of the table and across to the right, such that the highest ones are going to be right over here in the vicinity of the halogens. Okay, if you think about this, it makes total sense why. Right, first off, we go far over to the right side. We have a relatively high effective nuclear charge, so the pull on any electron that is being added will be strong. And then the other thing about this, if you look at this, is it will complete the shell of it, right? We know that they take it in and it's going to complete the shell, so it has a space available that it can hold it pretty well in that same orbital, so they're going to have very high. If you go over to the noble gases, however, they have a horrible, very low magnitude electron affinity, and the reason is they don't want to add one, because if they added one, they would have to put it out in an entirely new shell, right? So if you were looking at neon, which is 1s2, 2s2, 2p6, it would need to add a 3s1 electron, and it really doesn't want to do that. Okay, even sodium doesn't really want to have that electron. It happily loses it, very low ionization energy, and it has an extra proton that neon doesn't. So that's why we're going to increase as we go across to the right, but the noble gases are going to remain extremely unwilling to add an electron. Okay, so in general, you're going to have a better electron affinity as you go towards the right. You're also going to have a little bit better electron affinity as you go towards the top of the table, and that merely has to do as well with the fact that you're adding it closer in, and so the magnitude of the electron affinity would be a little bit higher. But realistically, the more important trend here is going left to right.